So let's try the first question over here. Okay. Now, so we have a electrochemical cell. Okay, it's going to be constructed using two half cells. Okay. So you have this. They want you to find out the material used for the electrode. Now you can see roughly now. Okay, when they ask questions on electrochemistry, they are asking you what type of electrode that is being used. Okay. So you can see in this half cell. Okay, if there is going to be both aqueous, then the only electrode that we use is going to be platinum. Okay, so please take note of that. And then when you have aqueous and metal, okay, cell, then the electrode that we need to use is going to be the metal itself, which is going to be the aluminium. Now, if they have used, for example, aqueous and gas, okay, aqueous and gas, for example, H2 and then H plus, for example, again, okay, the electrode that we are going to use is going to be platinum. Okay, please take note of this. I don't think so they will ask you why. Okay, but if they ask you why, then you just tell that platinum is inert and it is able to conduct electricity better, something like that. Okay, that will be the best answer. Now, the cell is operated at a standard condition. Okay, and then aluminium half cell also standard condition. And they have mentioned that this, okay, SN4 plus is 0.3, and this is going to be SN2 plus is 0.15. So basically, they are not in a standard condition. Now, if you are going to use, if you are going to calculate the electrode potential where they are not in standard condition, then we use the Nernst equation. Now, this Nernst equation, in the past, okay, what we have done, we ignore the reduced form, okay, because why? The reduced form is going to be the metal. Okay, I hope you can recall all this. Okay, if I have, like, for example, copper 2 plus 2 electron to become copper, I am only going to use the concentration of copper 2 plus. That's going to be the oxidized form. Now, it is very important to find out which one is oxidized form, which one is going to be reduced form. So here, when you look at plus electron, anything that is going to be plus electron, you see oil rig. Okay, reduction is going to be gaining of electron. So this is going to be reduced. So this is going to be the copper is going to be the reduced form. Okay, please remember. So copper 2 plus is being reduced and copper is the reduced form. And that's why copper is not included if we use Nernst form, because copper is metal. There's no point of looking for the concentration of copper. So that's why we just say log oxidized form. Okay, but here we have to include oxidized and reduced because both of them, okay, are ions. Okay, they are ions. So here, okay, use the Nernst equation. I think you just make sure you know the equation, the Nernst equation. Okay, the E standard, okay, 0.059 divided by Z, which is going to be the charge. Okay, in this case, there are 2 electrons being used, so this is going to be 2. Yeah, so please take note. Log oxidized form divided by reduced form. So you need to know which one is going to be oxidized form, which one is reduced form. In that sense, you need to write down SN4 plus, SN2 plus. Okay, so this is going to be plus 2 electron to give you SN2 plus. And you can see that this is going to be adding electron. So it's going to be gaining electron. This has been reduced. The SN4 plus is reduced to become SN2 plus. So this is the reduced form. Okay, please take note. SN2 plus is the reduced form. So therefore, okay, when I use the reduced form, okay, this one will be 0.15, and this is going to be the oxidized form is 0.3. That's why you get 0.3 divided by 0.15 log 2. Why this thing is going to be very important? Because students tend to think like this. They think, oh, SN4 plus 2 electron, this is going to be reduced. Also, this is going to be reduced form. Wrong. Okay. Please take note of this very carefully. So once you do that, okay, when you calculate, you will get positive 0.16. Now calculate the E cell, very easy also. Okay, look at your data booklet. Okay, you will see that negative 1.66, 0.15. The one that is more positive will move forward. This is moving forward. This will move backward. Okay, so this will be 0.15. That one that goes backward is going to become plus 1.66. So the E cell you just need to add. Okay, when you add, you are going to get positive 1.82. Okay, very easy this part. And then writing the equation for the overall cell, yes, based on how you calculate, this is going to go forward, this is going to go backward, balance the electrons, okay, balance the electrons, okay, and then you cancel the electrons and you will get this. Okay, quite easy. Okay, quite easy to get this answer. Okay, but what is going to be a bit difficult is this part. Yeah, please take note of this equation, Nernst equation. And I'm trying to relate with the metal because in the past year papers, in the previous questions, we always have been dealing with copper and copper 2 plus or any kind of metal. Okay, so we always use this form. Okay, E equals to E like this, and then plus 0.059 divided by Z. Then we put log, and then straight away the ion that is available. Okay, which is the oxidized form. Okay, but they will always tell, okay, this is going to be the amount of copper or something, but we don't actually look into the copper. We only use the copper 2 plus. Why? Because it's going to be the oxidized form. The reduced form is the metal. They are going to be constant concentration. We don't include them. Okay, but now it's going to be slightly different, which is important as well. Okay, please take note. Now, aluminium is produced industrially by electrolysis of melt containing large amount of aluminium ions. Okay, so this one is going to be Al3 plus 3 electron to give you Al. Calculate the mass of aluminium that is obtained. Okay, this one is quite easy. Yeah? Q equals to IT. So 300,000. Okay, time, okay, must be in seconds. Okay, 24 hours, change it into minutes. Okay, and then after that, change it into seconds. Okay, you calculate this and you will get, okay, let me calculate. .592 times 10 to the power of 10. Okay, column. And we know that, okay, according to the equation, 3 Faraday can form, okay, 1 mole of aluminium. 3 Faraday is 3 times 9, 6, 500. Okay, you should remember this already. Okay, will form 1 mole. So 3 times that. 289,500. 1 mole. So if it is going to be 1 column, 1 divided by 289,500. I want to calculate for this. So times only. So I'm going to have 1,289,500 times 2.592 times 10 to the power of 10 moles. Okay, if you calculate that, (89533.68 mole. Okay, then you need to change it into mass. Okay, so aluminium. Okay, the AR for aluminium, you need to find out. Aluminium is 27. Okay, so N equals to M over AR. Okay, M is going to be just times 89533. This is going to be in gram, 2417409.326 gram. So if you want to change it into kilogram, maybe 2417.4 kilogram, if you want to leave it like that. Okay, let me check the answer key. Two four two zero. Okay, they change it into 3 significant figures. Okay, but there is no mark deduction. Okay, if you don't change it. Okay, so 3 significant figures. Okay. Oh, they mentioned over here. I missed this. Yeah. So they mentioned it must be 3 significant figures. Okay. So cannot leave it like this. Okay. 2420. Okay, kilogram. Now explain why chromium metal cannot be obtained, okay, by electrolysis. Let's finish this. Now, chromium, if you look at your data booklet, you are going to get negative 0.91. And then here, when you do electrolysis, dilute aqueous chromium sulfate. I think this is IGCSE also. Sulfate, okay, you cannot electrolyze, okay, it's a very big ion. So what happened is going to be, if you're using chromium metal, okay, the only thing that will go and attracted to the cathode, okay, the cathode, the one that will be attracted to the anode, okay, will be the anion. It's not the sulfate ion. It's going to be the, hold on, it's going to be why chromium metal cannot be obtained, okay, by electrolysis. So if it is going to be Cr3 plus, okay, plus 3 electron, okay, and then dilute aqueous chromium sulfate, okay, so we are going to use chromium ion, okay, and another thing that we are going to use is not the sulfate, we are going to use the hydrogen ion, okay. So why chromium metal cannot be obtained by electrolysis of dilute aqueous chromium sulfate. So the dilute, okay, the dilute over there is going to be, we need a positive ions over there. So we need the positive ions that we need, okay, is going to be the H plus. So we want to find out, okay, whether you are going to get chromium metal, okay, or whether you are going to get something else. So when I use this, okay, what is going to happen is, I know this is all at the cathode, yeah. So I know what's going to happen. Basically, when you have the Cr3 plus, you have, you can see this is more positive, okay. So this will go to the forward direction, and this will go to the backward direction. So it means you are going to use up the chromium metal, not forming the chromium, okay. So how do I explain over here? Okay, you can say that hydrogen gas is formed, okay, hydrogen gas is formed, and tell why, okay, because the E cell, okay, is more positive, okay, and chromium metal will be used up, or chromium metal is going to be chromium metal is going to change to Cr3 plus, so it's going to be oxidized. Okay, that will give you the 2 marks. Okay, refer to the marking key. The marking key is telling that, okay, please, they also ask you to write down the E cell, that is going to be the 1 mark, okay, and then the moment you say hydrogen is formed, or hydrogen ions easier to reduce, or hydrogen has positive E cell, then it's enough already. Okay, so that's it for today. Okay, so is there any question? Number 2. Now, question number 2 is going to be the ClNO2 reacts with NO, and equilibrium is established. Okay, in each of the molecule, nitrogen atom is bonded to chlorine atom, and bonded to each of the oxygen atoms separately. So this one, what they are trying to say is they are telling that the oxygen and oxygen don't bond together and then you try to join with the nitrogen. It doesn't work that way. So they already telling us that, okay, it's not in that way. It means that they are telling that nitrogen is going to be the center atom. Okay, nitrogen is the center atom. So I put the nitrogen as the center atom. And nitrogen, okay, is going to be from group 15, so 5 valence electron. So if I draw, okay, 5 valence electron, and then I have oxygen, so I also draw oxygen, and I have another oxygen, so I draw oxygen, and then the Cl is going to be group 17, 7 valence electron. So the first thing that I can draw is going to be the for Cl, okay, 7 valence electron. So you need to have 1 electron to be shared automatically there. Now, out of 5 valence electron, okay, you give 1 electron, so you have only 4 electrons now. Now, please also take note that oxygen, they are all group 16, so they have 6 valence electrons. So here, maybe I'll use different way to, maybe I'll use a different pen, yeah. So here is going to be 6 electrons over here. So I need to figure a way, okay, how do I share the remaining 4 electrons, okay? So here, when the easiest way is to say, okay, maybe I can give form a coordinate dative bonding, okay? I can form a coordinate dative bonding, or okay, that is not the first thing that will come in our mind. Okay, normally what we will think is, okay, oxygen 6 electrons, so they need 2, nitrogen will share 2. Okay, that is the first thing that will come in our mind. So I will use that method. So I will erase only this part. Hold on, yeah. I'll just draw again. Okay, I will bring the 2 electrons here. And then nitrogen, they will share 2 electrons here. There is a double bond. So now you see nitrogen have utilized 3 electrons. So you still have, okay, another 2 electrons, okay, for the nitrogen. Now the 2 electrons, okay, either I can form another double bond, okay, I can form another double bond with the oxygen here, or I can do dative bonding. Now, whether I'm going to form another double bond or dative bonding, it depends on the total number of electrons surrounding the nitrogen. Now you see here, I still have another 2 more electrons, so I will put another sorry, a dot. It's supposed to be dot. I put it as dot here. Hope you can visualize this. I have another 2 electrons from the nitrogen. Now, so if I count the total number of electrons, I have 4 electrons and another 2 electrons shared with the chlorine. So I have 6 electrons, okay, surrounding nitrogen. In order to reach that octet structure, I need 8 electrons. If I go and share double bond to make a double bond over here, I'm going to get another 4, which is going to be 10 electrons. I don't want that. So it is better, okay, to form a dative bond. So give them directly that electron, the 2 electrons, give them directly. This is how you determine that whether there is going to be 1 dative bond and then there is going to be a double bond and 1 single bond for Cl. Okay, this is the criteria. Okay, the criteria. How did I end up with this structure? Basically, it depends on the question itself. They already give you. Okay, it must be a center atom. Okay, if they didn't give, then it's going to be difficult. But this is how it's supposed to be. Yeah. So I hope this one is clear. Now, the reaction between Cl NO2 and NO is first order. Okay, with respect to each reactant. Write the rate equation. So write the equation first order. Okay, make sure there is K. Okay, K is going to be the rate constant. Write down. Then deduce the unit of the rate constant. Okay, so I deduce the unit. Okay, rate is going to be, they say mole. Okay, you can see my working over there. mole dm negative 3 per second. Then this one is going to be concentration to the power of 2. So if I want K, I divide that. Okay, when I divide, okay, I cancel this. Okay, this one will become 1. So it's going to be per second, and then mole dm here. So when I bring them up, it will be mole negative 1, and then dm to the power of 3, and then per second. So this is how you do. Now the next is going to be very important. State and explain whether or not the reaction could take place in a single step. Now, I want you to really understand about the slow step, yeah? The slow step, okay, because normally when we write the equation, we know that, okay, the slow step, okay, must have all the reactant that has been included in the rate equation. That is very important. So here in the rate equation, both of them are first order. It means that the ClNO2 and NO must appear in the slow step. That is very important. They must appear in the slow step. Now, if I write down if they appear in the slow step, okay, is there a way to write the equation so that there is only a single step? So I write down, I think like ClNO2 plus NO supposed to give me directly this one. Okay, so I try to figure out, okay, maybe I was thinking, or you separate over here, the Cl will join with NO, and then the Cl, okay, will join with NO, and then the NO2 will stay outside. Now, when I write this equation, when I try to balance this equation, you will notice that each of them is going to be 1 mole, 1 mole, 1 mole. Now, if let's say you write and it happened to be one of the reactant, instead of giving 1, it happened to be 2. Please take note this. If that is 2 in the slow step itself, your rate equation is supposed to be rate equals to K NO to the power of 2 and then ClNO2 automatically. Okay, please remember this. Okay, it will automatically follow that, okay, in the slow step. So because normally we don't actually refer to the actual equation, it is depending on the experimental data, but rate equation follows the slowest step. So if you have the number in front, okay, there is a number, okay, if there is number 2 is involved, let's say you happen to do and then there's number 2 there, you cannot do this in a single step. Okay, you cannot do this in a single step. Therefore, you might need to have another step and so on. In this case, because the number of moles is going to be the same, okay, we can do that. Now, please take note, there is less questions on this. Okay, we don't have a lot of resources in this. Therefore, it is important, okay, to learn about this because this is very important, but they don't ask all the time. Okay, they don't ask all the time, and it can be very confusing. So I want you to focus in this kind of question. Okay, of course, they just ask a simple question here. Okay, but in the past, okay, you see, they ask you about write or predict the slowest step or predict the steps, okay, that can happen. Okay, or write it down in 3 steps, including the slowest step. Okay, and then you write it down and then suggest or something. So when you do the suggestion, okay, it is important, okay, when you have the rate equation and then you have the reactant, okay, in the rate equation, if they are there, okay, then you must include them in your slow step. For example, let me give you one example. Okay, let's say my rate equals to K and then A to the power of 2 and then B to the power of 1. And I want to predict, they said this reaction can only undergo using a single step, for example. So let's say the reaction is going to be A plus B to give you AB. This is the equation. So I need to predict. Okay, I need to predict how what are going to be the steps. So when I see there's going to be A2, okay, so it means that it's supposed to be my slowest step, supposed to be 2A. You must start with 2A because it's to the power of 2. Okay, 2 moles. Okay, 2A must start with B. Okay, and you will get AB. Okay, must be with something because it's not a they are not complete. Okay, they are not complete. So maybe what I will do is, okay, I will include something else. Okay, let's say I'm just I don't know, I'll just give you one example here. So maybe I include plus C. Okay, when I have plus C, then I will have another one as AC. Okay, I'm going to have another one as AC. So what I need to do is I need to eliminate, okay, I need to eliminate the extra, okay, let's say there is C over here. I'm not sure. Basically, I need to eliminate, okay, the AC. So what I need to do is I need to try to eliminate, okay, so that I get this equation. I couldn't really write it down, okay, but I hope you understand what I mean by, okay, there is going to be, I need to really put this 2 over there if I have 2 over here. Okay, this is very important. And it is also important your slower step must have B. Okay, must have B because they are there. Okay, but the others, okay, can come in, and your work is to try to come up with steps, okay, to eliminate the others. Like for example, come up with a step to add with C. Okay, come up with a step to eliminate the AC. Okay, to eliminate this AC. So what I can think is maybe you plus with another to give you another AB. Okay, maybe you plus with another B. Okay, so AB plus C. Okay, when I do this, when I add this equation, AC will cancel, and then the C will cancel, and I will have 2A plus 2B to give me 2AB, so which is going to be A plus B to give me AB. I hope you can see the relationship over here. So I came up, okay, with a step, okay, with something, okay, I came up with something that it means I use the add C. The C maybe it can be in form of a catalyst. Okay, the C it can be catalyst. The catalyst is going to be reformed again. So I have something like this. Okay, so please take note. Okay, how to relate this. Okay, how to relate this with slower step. Okay, I hope you can figure out a way. Okay, but the idea is your slower step. Okay, the number 2 over there is dependent on the number 2 over here, and it must be shown over there. Now the next question, okay, this one was a bit confusing, okay, but again, if you try, okay, it makes sense, okay, it makes sense because they say that an experiment, okay, they have the initial concentration, okay, 2 times 10 to the power of 4, so I just put the initial concentration over there, and then a large excess NO is used. The initial rate, okay, they have given the initial rate. Normally it's found through the tangent because this is concentration against time graph. Okay, so they have given you the initial rate, and the rate is assumed to be constant. Okay, so they say the rate is assumed to be constant. Do remember this one just now they mentioned that this is first order. Now if it is first order, okay, the rate is not constant. Yeah, you can see here rate, if it is constant, is going to be for 0 order. Okay, I hope you remember this graph. Rate graph, okay, for 0 order, then the rate is going to be this line. If it is first, okay, it's supposed to be like this. This one's supposed to be like this. But this is a graph, okay, for concentration against time. So always remember, for concentration against time, the graph supposed to be like, if you're talking about the reactant, okay, this is going to be for 0 order. And then for first order and second order, it's supposed to be a curve. Okay, it's going to be a different kind of curve. Okay, depending on the, you can use the half-life method to identify which one is which. Okay, because the half-life method is going to be half-life is going to be constant for first order reaction. Okay, please remember this. Now, but here they are asking you to assume. Assume is going to be some sort of a zero order reaction. Okay, that is what they are asking you to assume. So if they ask you to assume it's a zero order, you see here they say it's constant. So it means assume. If it is assumed zero order, then you need to have a graph that is supposed to go down like this. It's a straight line graph. Okay, it's supposed to be like this. But in reality, it shouldn't be like that. In reality, it's supposed to be like this. Okay. Now, I know like that. So I need to figure out, okay, how do I draw? From where I get this? Okay. I know that, okay, if it is going to be the rate is constant, I can calculate, okay, the gradient. Okay, I can calculate the gradient because the initial rate must be represented by this rate also. So my thinking process is like this. If I have something like this, okay, if let's say there is a graph going like this, okay, if I know what is going to be my my gradient, okay, the gradient supposed to be 1 times 10 to the power of negative 4. And I know that it's supposed to go until 0.2. I know it will stop somewhere at 0.2. So what I can see is if I want to count the gradient, I know that this is 0.2. I just need to find out what is this. Okay, I just need to find out what is that. And you're supposed to get y divided by 0.2, supposed to be the gradient. And the gradient, they already mentioned 1 times 10 to the power of negative 4. So your work is just to find what is y. Y is going to be 0.2 times this. So it's supposed to be 0.2 times 10 negative 4. Okay, it means that this is supposed to be 0.2 times 10 negative 4. If you look at the graph again, okay, each of them, okay, you can see here, this is going to be 2.6, okay, 2.6, 2.7, 2.8, 2.9, then after that 3. So I just want to see, I just want 0. It's supposed to be, here is going to be 0.1. Okay, every one step is going to be 0.1. So I just want to find out, okay, it's supposed to decrease how much. I think I made a mistake also. Okay, when I draw, okay, it's supposed to be 0.2. Okay, 0.2. So when I draw for 0.2, okay, let me share the screen again. Hold on here, guys. Okay, I know it's going to be time. Okay, let's continue again. So here, okay, when I see this one's supposed to be 0.2, okay, so I know that every one of it is 0.1. So I know that from 0.2, so here this is 0.1, and then it's supposed to be, this one is 0.2. So my graph supposed to be from here, it's supposed to end over here. Can love it. So that I get something similar to this one, 0.2, and then y I found out is 0.2 times 10 negative 4. So why is that? Okay, please take note. Yeah, every two box. Okay, every two box is 0.1. So 1.6, 1.7, 1.8, 1.9, and 2. Okay, so I want 0.2. So I need total 4 boxes here. So 4 boxes here. Okay, once you get that, okay, deduce the concentration. Okay, it's already 12. Anyway, deduce the concentration of NO2 product at 0.2 seconds. This one I don't agree with this question. Okay, it's a very weak question. Why I say it's a weak question? Because okay, if you are reacting with 0.2 times 10 negative 4, if let's say we assume the volume is going to be 1 dm cube. Okay, so they are going to react. Okay, if you use the ice method, yeah, so this one is going to be minus with this, so everyone is going to be 1 mole. So imagine earlier NO2 is 0, so NO2 will also act with this same value, but do remember that is 0.2 times 10 negative 4 is moles. Okay, but they are asking the answer in form of concentration. Now do remember, just now they add this stuff in excess. Even you assume this is 1 dm cube, we don't know how much they added here. So it's supposed to be total volume. So I don't really agree with the question, because it's they are assuming the answer is this. The answer is going to be 2 times 10 negative 5, which is the 0 plus 0.2 times 10 negative 4, which is going to be this one, the number of moles. Okay, but they're asking for concentration. They divided it with 1 dm cube, which I don't agree. Okay, which I don't agree. It's quite a weak question. Okay, but I already told you how they reach the answer. Okay, the answer is reached by just counting the number of moles, then they refer to that number of moles. That's it. Okay, and then after 20 seconds, the concentration remains constant. Now, normally when something is reacting, it will become 0, because do remember, this is reacting with NO. Okay, so the NO is excess. So normally this was supposed to reach until 0, but they say suddenly it became constant. So it can only become constant if it reach equilibrium, and you can double check, because this is going to be a reversible reaction. So therefore the answer must be reach equilibrium. And I just wanted to do question 3 also, but we don't have enough time. Okay, so I will stop over here. You guys can continue. So please join the YouTube link, yeah, the live version. Okay, then that's it for today. Any question before I end? So you see the next part is going to be what is meant by the term entropy of a system. So entropy of a system is going to be a measure of disorder or randomness of a system. So you can either answer your based on a measure of disorder of a system, or you can say a measure of randomness of a system. Okay, but do remember, mention of a system. Okay, this is very important. Now the next part is going to be state and explain whether the entropy change, okay, of the following is going to be positive or negative. So if it is going to be positive, generally it is going to be since it's a measure of disorder, okay, they are going to become from order to become more disordered. Okay, so if this is negative, means disorder to become ordered. So now, okay, you see here, they say do not consider the entropy change of the surroundings. So don't bother about that. Just look at what is happening for the liquid. If they say liquid, just look at the liquid alone. Now the liquid water, okay, at 80 degrees Celsius is cooled to 60 degrees Celsius. So what is going to happen, because there is going to be decrease in the energy, okay, they are going to become much more ordered. Okay, so if they are going to become more ordered, then you are going to write it as negative. So it will become negative, okay, because now the molecule will have less energy. And if you want, you can say that they will become more they are going to become closer to each other, whatever that you want to mention. But the marking key will accept negative and the less energy. Okay, this is going to be the one that will be accepted. Now, the next is going to be the solid calcium chloride is added to water and the mixture is going to be stirred. So this is going to be when you add this solid, okay, something, and then you stir them, what happens? They dissolve. So when they dissolve, basically they are going to become more random, okay, because solid is going to be very regular. So when they are mixed with water, they are going to be more random. So therefore the entropy change is positive. Then the explanation that you're supposed to give is going to be the solid dissolved to become aqueous ion, and this aqueous ion, they are more randomly arranged. So you can actually mention about that. As long you mention about solid is changing into aqueous ion, okay, that is very important also. So please take note, you must have these points. Now the next one is going to be the change corresponding to lattice energy of calcium chloride. Now you need to know what is lattice energy. Lattice energy is going to be the gaseous ion, okay, of the calcium. Like for example, if I write down what is going to be, how do I write down the lattice energy of this? Ca2 plus gas plus 2Cl minus gas to give you CaCl2 solid. This is going to be the lattice energy equation. So this is going to be from gaseous ion, they are going to become solid. So you need to mention, okay, gaseous ion to become solid. So it's going to be negative because they are going to become more ordered, from less order to become more ordered. So I have written over there. But I want you to understand 3 marks over here. Okay. So it's not important whether you know how to say, okay, negative, positive, and so on. It also matters on how do you define them. And you cannot simply whack the answer saying that, oh, negative, this is going to be from, they have, like positive means from regular, they become less regular. Negative, less regular, okay, they become more regular, for example. You cannot say that, okay, you need to explain properly. So here you need to talk about the energy. Here you need to talk about solid changing into aqueous, and you need to relate with the definition of lattice energy. The gaseous ion is changing into solid. Okay, the next, okay, this is also something that I learned also. Okay, I think in the past they never asked what is going to be the full name of this. Okay, this is first time also. So even I almost made the mistake. Okay, I wrote it as Gibbs free energy because I think that is how we define them. How do we always use them? But in the marking key, they are emphasizing on this change. Okay, so you how do I know when to use change or something? Because do remember the formula is always the triangle this and then triangle H and this one. The triangle, okay, represents change. So the full name is supposed to be Gibbs free energy change. If you want to include, this is going to be this one, this symbol, then it's supposed to be standard. So the full name, if you want to include, is supposed to be standard Gibbs free energy change. Okay, standard Gibbs free energy change. So please take note, okay, how to define them. This is triangle, it's a change, Gibbs free energy. This is standard. Okay, so it's going to be standard Gibbs free energy change. Now describe how the temperature of the reaction becomes spontaneous, okay, when calculated. Include an equation for your answer. Okay, this is the equation. Okay, I told you to remember Mr. Gopi is not that hot or something like that. So you can actually remember this. Okay, and then after that, okay, when I want to find out when it's going to be, what is going to be the temperature when it becomes spontaneous, it means it becomes spontaneous the moment they become negative. Okay, Gibbs free energy have to be negative. So what they will do is, okay, to find the minimum temperature, they will replace that Gibbs free energy as 0. So you need to write down as well, describe how, okay, you represent the Gibbs free energy as 0. Okay, then you calculate using the enthalpy change, using the entropy, okay, of the system, and then using the temperature over there. Okay, you can calculate what is the temperature when this is going to be 0. Okay, you can calculate. So that this entire 2 marks question is based on that. So what you need to mention, okay, calculate the temperature when Gibbs free energy change is 0. Then you calculate. So sir, I need to leave a little bit. Yeah, please, Victoria, later what time you need to leave, you just leave. Yeah. Just now, Victoria, why you didn't tell me it's 12:30 only?
Sir, I thought because teachers need to go first. I didn't know.
No. I saw this announcement last week. So in my mind, I put it as 12. Then I will miss 30 minutes. So they announced as well, but since I already put in my mind, okay, so I just thought it's like that. So anyways, my mistake. So anyway, okay, if you need to leave, you leave, but I'm almost there. I will try to cover up to here. Okay. Here is going to be phenyl ethanol. Okay, it's a important chemical with many uses. So when I see this, they say it can be synthesized by using benzene as the starting material. So when I have benzene, okay, when I have something added to the benzene, there are only few reactions that can directly go to the benzene, which is going to be the electrophilic substitution, like nitration. Okay, when you want to add methyl group or acyl group, then it's going to be acylation. Okay, Friedel-Crafts acylation or alkylation. There are only few things can happen. Okay, even like oxidation, it is for methyl benzene. So here, if you have like this particular thing, so you know automatically it's going to be Friedel-Crafts reaction. So I will use the acyl chloride. Okay, acyl chloride. So just take this one. Okay, just this part. So you need to have Cl. And in order for the Friedel-Crafts reaction to happen, you still need to have the how to say, it's a catalyst. Okay, it's a catalyst, not the halogen carriers, they are catalysts. Okay, in this sense. So this is catalyst. So once you have this, okay, you are going to write down, identify other regions and describe essential conditions. So you need catalyst. And this one, okay, we name it as 2 carbon. So it's going to be ethanol chloride. So if I have 3 carbon, for example, and then like this, how do I name this? This is going to be propanoyl chloride. So acyl chloride, okay? So propanoyl chloride, butanol chloride, and so on. So it is important for you to know this name, okay, because identify. But again, if you just want to write the this one, since they say identify only, still okay. Okay, but I'm just worried if they ask you to write name the reaction, then you can't even write down AlCl3. You need to give them the name aluminium chloride, okay, catalyst. So please be careful of that. Okay, so here phenyl ethanol. Okay, I noticed that this is phenyl ethanol is going to be, this is R group, another R group is basically ketone. Now, this ketone can be treated with 3 regions. So I was thinking why I identify that. Maybe even before reading the question over here, I need to put it in my mind. Okay, ketone. Ketone, what are the reactions of ketone? Okay. Of course, it doesn't have any reaction with any oxidation. Okay, like for example, no reaction with Fehling. There's no reaction with Fehling Tolan. Okay, you cannot oxidize ketone further. Okay, so I was thinking, okay, maybe okay, let's read the question. So I identify first, then read. So there's no, I don't think so there will be reactions related to that, unless okay there is one reaction like uh if they say carbonyl group, okay, they have some general reactions, okay, then they will talk about that. So here, okay, if you look at chlorine gas at 10 degrees Celsius, and then with the presence of UV light, okay, UV light automatically, they cannot come directly to the benzene ring, so they will have free radical substitution. So they will replace or substitute any of the H, or it can substitute completely. Okay, but here I think better to substitute only one, because even in the answer key they substitute only one. But do remember, they say structural formula. Even the answer key, I don't think so. The answer key is a bit accurate there, because it's supposed to be structural formula. It's supposed to be C6H5 CO and then CH2Cl. This is going to be the structural formula. Okay, this one I'm just drawing for you to see. Okay, but in the marking key they give something like this. I don't think so it's a very suitable way to say. Okay, this is supposed to be correct. So it's a free radical substitution, and then they have a mixture of nitric acid, okay, and sulfuric acid at 50 degrees Celsius. In our textbook it's written 55 degrees Celsius, so please take note, because it's 2019, quite recent. Okay, so please take note, maybe you can just give any answer between 50 to 55 degrees Celsius when it comes to nitration reaction. So nitration reaction is going to happen. What is important is, okay, this is going to be a group that is going to be electron withdrawing group. Okay, electron withdrawing group. So if it is electron withdrawing group, they are not going to be 1, 3, 5 directing. They are going to be 2, 2, 4, 6 directing. So I know this position is going to be activated. This position is going to be activated. But okay, I reserve myself, because I don't want to write another NO2 over there, because they didn't say that it is going to be reacted until complete, or they didn't say it is in excess. If they didn't say until further nitration or something, or complete nitration, just choose only the beginning. It means only the beginning part. Even here I didn't use or substitute until complete, so just the first step. Okay, just the first step. So but it is important, okay, to substitute this at position number 3. If you go and substitute at different position, automatically you will lose that 1 mark. Okay, automatically. Now the next is going to be the reaction with bromine water. Okay, the reaction with bromine water, here it doesn't happen. Okay, it doesn't happen. There is no reaction. Okay, so because of that, okay, there is no mechanism of the reaction also. Okay, please take note. Okay, so bromine water, okay, even bromine water, they didn't say bromine gas, okay, with any halogen carriers or something. No, so it doesn't react. Okay, it doesn't react. Now, here, okay, I want to show you phenylethanol reacts with ACN. This is what I told you, the one I prepared just now, ketone. Now, ketone or aldehyde, okay, they can react, okay, the carbonyl group, they can react with this HCN, okay, with the presence of NaCN. This one, you please read again. This one is prepared, okay, HCN is prepared in situ, okay. So, I think the reaction is done with the NaCN plus ACN. Okay, so you are going to get the CN ion over there. They are prepared in situ, okay, in the textbook, within the same reaction vessel. They put everything together. Okay, when you put everything together, what will happen? Okay, the mechanism of this reaction is going to be the carbonyl group will react. Okay, when the carbonyl group react, okay, so in this case, you are going to be using nucleophilic addition mechanism. Okay, carbonyl group will have nucleophilic addition. So this is what they want, okay, you to write the mechanism, okay, using the curly arrow, so which is very important. So at the phenyl ethanol, okay, so you have if you have this, okay, what will happen, okay, what will happen? So you need to write down, okay, in terms of first, okay, this is going to be nucleophilic addition. So if it is nucleophilic addition, you need nucleophile. Okay, nucleophile is attracted towards the nucleus. So currently, okay, it's not going to be attracted, okay, to the nucleus, because nucleophile supposed to be attracted towards protons, so they must have negative ion. So in this case, the nucleophile must be Cn minus. Okay, how do we get Cn minus? Because the HCN and the NaCN, they will give you the Cn minus. Okay, they will give you the Cn minus, especially from NaCN, they will give you Na plus and Cn minus. Okay, so this Cn minus is coming from NaCN. So this Cn minus, okay, must be attracted towards something that is positive. Okay, so how do we need? How we need to show them? Okay, so how do we show? You show like this. Okay, oxygen is going to be more electronegative. The electrons, okay, they will be moving towards the oxygen, so making it delta negative. When this is going to be delta negative, automatically this one will become delta positive, the carbon. When that's going to be delta positive, so now the Cn minus will come. Okay, so generally what is nucleophile? Nucleophiles, they have lone pair of electron ready to be donated. Yesterday I gave you this lesson. Yeah, so they are going to come over here towards the carbon. Okay, they will come towards the carbon, and they will form intermediate. Okay, so I will draw for you the intermediate, but now you see, by now you should remember how to draw intermediate. It's going to become something like carbon. Okay, there's carbon, there's oxygen. Okay, there's going to be CH3. So there's total surrounding the carbon, there's going to be 4 things. Okay, so I'll write down CH3. Okay, and then there is also Cn attached to it, and I have O. Okay, and then I have the O is going to be O minus here, and then I also have this. It's still okay if you draw like this, 90 degrees, to show 90 degrees. But if you want to draw to show it's a tetrahedral, also fine. Okay, it's fine. Now, what's going to happen next is going to be, now you are going to have this HCN. Okay, this HCN just now. Where is HCN? Yeah, HCN. Now, HCN, okay, do remember, they are going to be, okay, they are also going to be, what happens, the electron from here, they will go over here. So there is going to be heterolytic fission is going to happen. Okay, heterolytic fission is going to happen. So this is going to be delta negative, this is going to be delta positive. So what's going to happen, this electron from here, they will go towards this H. Okay, so you are going to get, okay, I'll just draw C, this is going to become OH, and this one will stay. Okay, this one will stay, and you will have Cn plus Cn minus. Okay, you will get this. So these are the product. Okay, so you are going to get something like that has OH and then the nitrile. Okay, what is important over here, you notice that there is an addition of carbon. Okay, carbon has been added. Okay, so if this is what I want you to recall, that's why I put it here. You need to remember, okay, the moment you have this reaction with HCN and NaCN, you need to remember nitriles. Okay, they can also change. Okay, what are the reactions of nitriles? Okay, so please read further on this. The nitriles can change into carboxylic acid if, okay, you reflux with HCl. It means that this molecule can change into this. If they want to continue this reaction, okay, they will give you further question, then they'll ask you, okay, what will be formed. So you're supposed to get this. Okay, if you reflux with ACl, you are going to get this. Now, if this molecule, okay, if you want to react, okay, a reduction reaction will happen. You can change it into amine also. Okay, so you can use sodium with ethanol. You can have this molecule to be formed. Okay, I'll just put here amine. Okay, it's a bit messy, but please take note. COH, and then this one CH3, this one CH2, and then NH2. Okay, amines will be formed. So that is going to be extra thing that I want you to learn. Okay, but this is going to be the answer for that. And then the rest, okay, please do your own revision, because I wanted to just discuss up to here today. Okay, it's already 12:30 also. Any questions up to here? Jason, any question? Continue from here. So you can see the phenylethanol, okay, can be used as a starting material to make phenylethene in a two-step synthesis. Okay, and from what I can see here, okay, you can see it's a ketone. Okay, it's a ketone. R group, another R group is a ketone, and then you are going to change to something, and then that something is going to be changed into alkene. Okay, you can see alkene double bond. Now, to produce something, okay, related to alkene, okay, I know for sure, okay, I know for sure this one must be something related to dehydration, okay, because it's quite limited. Okay, what are the reactions that can give you double bond? Okay, so maybe if I have alcohol, then I can dehydrate. Okay, maybe if I have a halogen alkane, then maybe I can do elimination reaction. Okay, something like that. Okay, that's my thinking process. But I need to think about ketone. There are, for ketone, there's only limited certain reactions involving ketone. So you need to also remember that. I think for the ketone, I think if you look at the previous reaction, okay, for anything that is involving aldehyde or ketone, you have the one reaction, which is going to be the reaction with HCN. Okay, HCN or with NaCN. Okay, so this one is called addition elimination reaction. Please take note as well. So again, this is going to be nucleophilic addition reaction. So here, okay, when we look into this, okay, there is one reaction involving ketone, which is going to be, you can react with NaCN with ACN. Okay, you are going to get nitrile. Okay, now that reaction, okay, is not going to be suitable here, because you do this reaction in whenever you want to increase the number of carbon. Okay, you can see here number of carbons are the same, so you do not need to increase any carbon over here. So we need to think about other reactions. Okay, very less reactions involving ketone. Yeah, so one thing that I can think of, okay, is going to be when we learn about alcohol. Okay, when we learn about primary alcohol, okay, can be oxidized to it can be oxidized to become aldehyde. Okay, and aldehyde can be further oxidized to become carboxylic acid. Okay, and I also learned that, okay, secondary alcohol, okay, can be oxidized to ketone, and tertiary alcohol cannot be oxidized. Now, so now I have ketone over here. Okay, if secondary alcohol can change into ketone, of course there is a way to change ketone to become secondary alcohol. Okay, so this is going to be, we are going to change, okay, ketone to secondary alcohol, which is going to be we are talking about dehydration. Okay, sorry, it's not dehydration. This is going to be reduction. Okay, we are going to do reduction. Now, please remember, when it comes to reduction, okay, it is sometimes, okay, we can have situation like simple reduction like ketone to become alcohol, or aldehyde become primary alcohol. Okay, you can use any reducing agent. Okay, you can use any reducing agent, but whenever you are trying to reduce carboxylic acid to become primary alcohol, then you need a stronger reducing agent. Okay, please remember that. So the stronger reducing agent is LiAlH4. Okay, in dry ether. This is a strong one. Okay, we do not use the NaBH4 here. Okay, please remember this. So this one, okay, we have to use this. But okay, for this and this, you can use both LiAlH4 in dry ether or NaBH4. Okay, LiAlH4, NaBH4. Okay, you can use. So here, when they say identify the regions responsible over here, and before that, okay, when they are asking me to write down the structure, draw the structure. Now they didn't specify what kind of structure. Okay, display formula, structure formula. So when they don't specify, anything will do. Okay, so even you draw like this also fine. Yeah, so when you have this, okay, I know when I do the reduction, what's going to happen. The H is going to come over here, another H will come over here. Okay, so when you have that, okay, you are going to have this alcohol over there. So this is going to be a secondary alcohol. Okay, I wrote over there secondary alcohol. Then after that, okay, you are going to have the step number 2, which is going to be the dehydration. Okay, so anyway, the identify the suitable region for step number 1. Step number 1 is going to be, it's going to be a simple one, secondary ketone to become secondary alcohol. So you can use any of this, okay, LiAlH4, okay, or okay, you can use, okay, just give only one, okay, no need to mention both. Okay, so you can say or, okay, if you don't want to write down that, so you write down NaBH4. Now they ask you to identify suitable region. Okay, sometime, okay, they even add, okay, identify suitable region and condition, but that doesn't mean that they are going to give you 2 marks. Okay, in this case they didn't mention. Okay, in this case they didn't mention. Okay, one of the reason, most probably they don't mention, maybe students might miss out. Okay, especially for the NaBH4. So maybe I think they decided not to ask about the condition. Okay, but the condition, if they ask for condition, okay, in dry ether. Okay, in dry ether, and this one is going to be aqueous condition, aqueous, and then it is going to be room temperature, and I think this one is also room temperature. Okay, again, nothing will change over here. Okay, now identify a suitable region, okay, for step number 2. Now step number 2, this one is the in the beginning when we learn about hydrocarbons. Okay, we even in AS we have learned about this. Okay, if you check your textbook, okay, there are few things that they mention. Even in the textbook they mention about this Al2O3. Okay, they mention about this. This is going to be, you are using this, okay, and then you can change it into alkene. Now in the same textbook on the same page, you can see there is a question over there that they also included over there, where you need to know, apart from using Al2O3, you can also use concentrated H2SO4 to achieve this, or you can also use, okay, sorry guys, I got disconnected. Okay, but anyway, let me repeat again. So you need to know, okay, whenever you do this, okay, it's either you need to use concentrated sulfuric acid, you can use concentrated phosphoric acid, okay, or you can use the Al2O3. Okay, let me just double check for you the do you need to heat them up. Okay, give me a second. This one, if you want to check, it's going to be in page 230. Okay, so this is going to be dehydration. Okay, the catalyst that is going to be used is going to be Al2O3 catalyst, and it is going to be the reaction is going to take place when alcohol vapor is passed over hot catalyst. Okay, so passed over hot catalyst. So if you want to mention it's going to be passed over hot catalyst of Al2O3, it's possible. Okay, but again in the same page, okay, there is a question over there, okay, which is question number 6. Over there only you will see you can use, okay, we can use sulfuric acid and phosphoric acid to catalyze. Okay, but do remember they mentioned about the temperature also, okay, the exact temperature. They mention about 170 degrees Celsius. So please remember this. So it must be heated. Okay, it must be heated. So there is a question over here. Okay, let me see. Okay, yes, 180 degrees heat, sir. Yeah, correct. So this one is going to be heated. Okay, 170 degrees Celsius. Okay, and then for the prelims, okay, do we get marked if we write CONC instead of concentrated and RTP instead of room temperature? Now, when I see here, okay, when I see the marking key, they only write CONC. Okay, there is no instruction, okay, to deduct marks. Okay, but for me, don't take any risk. Okay, write full. Okay, write in full. RTP in the past also I never seen any questions, okay, where any marking key saying that deduct mark when RTP is mentioned. So to answer your question, possible, okay, possible, but I will not encourage you, okay, to do that. Okay, so this will be my answer for this. Okay, so concentrated, write in full. Even when I try to teach you also, I try to write it in full also. But again, it's relative. Like even for aqueous, I tend to put AQ. Still okay. It depends on your time. Okay, it depends on your time. If you're really rushing for time, then you put CO and C and so on. If you have time, come back. Okay, come back and then write in full. Okay, this is my suggestion. Yeah. So here, okay, heated. Okay, not 180. Okay, the one that I saw from the textbook is 170, and yeah, 170. And for this one, they just put hot, okay, in the textbook. Okay, so maybe, okay, if you have seen any like for example any other marking key or something, yeah, you can also use that information. But here, since they didn't ask you the condition, okay, we still put the region only. Yeah, so again, this is 1 mark. It can be still 1 mark, okay, but we can still ask you about the condition. Most probably the decision why they only asked the region, why they didn't ask the condition, means most probably because sometimes the students, when we give this 1 mark, we say N. Okay, it means sometimes students will identify region correctly, but the condition they are wrong and they are not going to be able to get that 1 mark. So to help students, sometimes, okay, the people who prepare the test paper, they will suggest, okay, let's only test the region. Okay, let's not test the condition, but the mark they maintain. Okay, this is a situation. But sometimes, okay, they feel that they need to really test the condition. Then they will test the condition. In this case, the condition is not going to be it's not given importance for now for this particular question. Yeah. Now, state the number of peaks, okay, of carbon-13 NMR spectrum of phenylethene. Now, phenylethene, okay, this is phenylethene. Let me erase this. Now you can see here, okay, how many different carbon environment, okay, that we have over here. So I have, this is going to be one carbon environment. This is going to be another carbon environment. Okay, the carbon is attached to hydrogen and benzene group. And then I have another carbon environment here. Okay, and then you can apply the symmetrical rule. Okay, this is going to be another carbon environment which is the same as this carbon environment. This is going to be another carbon environment which is going to be the same as this carbon environment, and this is going to be another carbon environment. So in total, okay, we have total of 6 carbon environments. And you can see now, okay, roughly when you do, I think 3 papers already, this is the third submission. So 3 papers, okay, you can see when I go through also with you, they always try to assess you on this, and 1 mark, okay, and another 2 mark, okay, related to this. So it's always like that. They are not going to ask you a lot, okay, they are not going to ask you a lot, but they will be definitely asking about this. Okay, now, so suggest the carbon-13 chemical shift ranges expected. Can you guys still hear me? Victoria, can you hear me? Okay.
You were lagging, sir.
Yeah, okay. I can see you all moving now. So anyway, okay, I think this one is okay, yeah. So I was actually mentioning about, um, please remember the chemical analytics part, okay, they will not give you a lot of marks, okay. So here you see it's they ask you, and then suddenly they came into analytics parts, and they just ask you about 3 marks question, yeah. So it's quite easy, okay. But again, okay, suggest, okay, they say here 2 marks question, suggest the carbon-13 chemical shift ranges expected for different types of carbon environment in phenylethanol. Okay, so I took the phenylethanol and I put it over here. Okay, so here I have a few carbon environments. Okay, what are the carbon environments? Okay, maybe this one. I also have this carbon environment, so maybe I can mention about that. And I can also see maybe this carbon environment or any of this carbon environment I can mention about that. Okay, so the carbon environment in benzene. Okay, so let's look at the in your period in your data booklet. Okay, what are the things that I'm going to look for? Okay, maybe the first one that I'm going to look for is going to be the carbon. Okay, this one. If I put it as number 1, the carbon which is next to carbonyl group. Okay, so this is going to be carbon next to carbonyl group. Okay, so I am going to expect, if I put for 1, I'm going to expect there is going to be a shift from 25 to 50. Okay, I'm looking for that. Okay, there will be a shift for 25 to 50. Why is that? Okay, so for what? Okay, for what? So that is going to be, okay, let me share the screen again, yeah. So maybe, Okay. So when you look over here, okay, we can see the first one is going to be the 25 to 50. That is going to explain about the carbon that is attached next to carbonyl group. Okay, next to carbonyl group. I am also going to see the carbon that is directly attached to the carbonyl group. So let's look at here. This is directly attached to the carbonyl group. So we are looking at 190 to 220. This one. 190 to 220 directly attached to carbonyl group. Okay, so another one more that I can select, maybe something related to this benzene. So look for benzene. So not this one. Okay, not this one. So something related to benzene. So this one. Okay, you see, it is going to be carbon. Okay, carbon that might be attached directly. Is either carbon double bonds or in arene. Okay, so this might be one of it. So 110 to 160. So this one, if I put here, any of this, okay, they will have that range. Okay, that is going to be 3. So this one is going to be 110 to 160. So this one you can say arenes, carbon in arenes. So here they say suggest. Okay, when they ask you to suggest, please suggest with reason. Okay, cannot simply suggest. Yeah, so please suggest the range and tell what is the reason. Okay, when they say here, okay, when they say chemical shift ranges for different types, okay, if possible, okay, they didn't say all, okay, but if possible, if they say something like this, at least, okay, 2 ranges must be given. Okay, so here, even in the marking key, you can see if you mention any 2 of here with they didn't even give you marks for reason. Okay, they didn't give you marks for reason, but I'm suggesting you to write down the reason. Okay, but here, as long you just give the correct range, okay, at least 2, then they will give you the full 2 marks. Okay, so this one you can get it, okay, from your data booklet, but make sure you select the right one. Okay, this is going to be carbon 13 NMR. There is also the proton NMR. So please be very careful which one do you select. Yeah. Now next, okay, silver sulfide. Okay, is going to be very soluble in water. Write very insoluble in water. Okay, so write an expression for the solubility product of Ag2S. So this one is Ag2S solid. Okay, they're supposed to give you 2Ag plus aqueous plus S2 minus aqueous. Okay, very insoluble in water. So write down the expression of solubility product. Now for solubility product, we only write down, okay, the expression for this and this. We do not write down for the solid Ag2S, okay, because the concentration is constant. So we write down Ag plus and then to the power of 2 and then S2 minus. So this is going to be the expression, okay, that they are looking for. And then they are asking the solubility, okay, is going to be 1.16 times 10 to the power of negative 17. So that is solubility, okay. So what is solubility? It means that, let's say if you dissolve, okay, if let's say the reaction is happening, if this one we take it as X, okay, if this one we take it as X, this is going to be solubility means, okay, this one will minus X. Okay, when you add water, this one will be the number of moles, so it's going to be minus with X. And then here, you are going to have something like plus 2X. Okay, plus 2X. Okay, I hope you can see. So plus 2X. Okay, my internet is laggy again. Okay, let's wait for a while. Jason, can you hear me now?
Yes.
Okay, so let me continue again. So talking about solubility, okay, so I will take solubility as X, okay. So we take it as minus X. So this one will be plus 2X, and this one will be plus X. Okay, that is going to be happen if let's say they dissolve like normal. So they actually have 1 mole, 2 moles, and 1 mole. Okay, so just like that. So here, if I put, if I want to calculate the numerical value of the solubility product, okay, so the KSP, okay, is supposed to be silver ion, okay, the concentration of the silver ion, okay, the silver ion is going to be 2X. So I put over there 2X, and then to the power of 2, and then here X. So it is very important, yeah, please take note of this, okay. 2 to the power of 2 is going to be 4, so X to the power of 2, then X to the power of 3. Okay, and that's going to be your KSP. So 4 times 1.16 times 10 to the power of negative 17 to the power of 3. And you will get the answer. Okay, so let me calculate also. You guys also calculate. Okay, when I saw that number, I was thinking I'm wrong. Okay, but again, just double check. Okay, just double check, and you will get, okay, 6.24 times 10 to the power of negative 51. Okay, so here they didn't say how many significant figures. Okay, so 3 significant figures must be there if it is not mentioned. Yeah. So here, okay, KSP is 6.24 times 10 negative 51. They want only the numerical value. Sometimes they will ask you to find the unit. If they ask you to find the unit, then you'll have another 1 more mark for it. Okay, so here is just a numerical value. Okay, doesn't matter. Now calculate the minimum volume of water needed to dissolve 1 gram, okay, of this solid under standard condition. So what you need to do is to find the number of moles. Okay, number of moles of this. So the number of moles is going to be 1 divided by, you calculate, okay, using the MR, okay, the MR is going to be 247.9. And you will get 0.00403 moles. Okay, so now, okay, using this number of moles, I need to calculate, okay, I need to calculate the minimum volume required, okay, to dissolve this. Now, if you want to dissolve this, okay, so we are trying to look into not the KSP, we are looking into the solubility. Okay, we have to use the solubility data. Now the solubility data is going to be 1.16, okay, times 10 to the power negative 17. Okay, so what I need is, okay, I need this 1.16 times 10 negative 17 equals to, okay, number of moles. Okay, so the number of moles is going to be 0.00403 divided by the volume that you need. Okay, so you just need to put it over here and then use the solubility. So V is going to be 0.00403 divided by this, and you will get the answer in dm cube. Okay, this one, if you do, you will get 3.5 times 10 to the power of 14. Okay, dm cube. So they didn't tell what is going to be the significant figures, but the data that I have over here is in two significant figures. Okay, but if you have 3 significant figures, then please include. So here I will write down 3.5 times 10 to the power of 14. The important thing is I am going to use solubility. Okay, I'm going to use solubility. So the data here, then you will calculate the volume. Now next, okay, this is going to be bromic 1 acid. It's a weak acid. So if it is weak acid, write down the equation HOBr. They are going to give you H plus and then OBr minus. Okay, so the Ka is given, and then you need to calculate the pH. Okay, so if you have that, okay, I think the best way is to write down what is Ka. Ka equals to H plus times OBr minus divided by concentration of HOBr. There are few assumptions that is going to be taken. One is, okay, we assume that the amount of moles that dissolve for HOBr is too little, so we take the initial concentration. Okay, and we also assume, okay, the concentration of this and this are the same because number of moles 1 and 1. Okay, so here I can just write down H plus, OBr minus is also H plus. I put like that, and I have, okay, use the assumption, okay, this one HOBr, and I have the Ka. So just apply the same formula. So 2 times 10 negative 9 equals to concentration of H plus to the power of 2, and then concentration of HOBr, which is given 0.2. So just find out what is H plus. 0.2 times 2 times 10 negative 9 square root . 2 times 10 negative 5. pH is going to be negative log concentration H plus, which is going to be negative log you will get the answer as 4.69, so 4.70. Next is going to be, okay, you are going to have something like a buffer solution. Okay, so you have potassium hydroxide, and then you are adding to HOBr. So we need to calculate the pH of the buffer solution, okay, that is going to be produced. So here, okay, the way to do this, okay, is going to be first, okay, I think better if you want to write down, okay, if you're looking for the pH, okay, first find out what is going to be your number of moles of KOH. Okay, number of moles of KOH is going to be 5 times 0.2 divided by 1000, and you will get 1 times 10 negative 3 moles. So when I have potassium hydroxide, so potassium hydroxide, they give you K plus and OH minus. HOBr gives me H plus and OBr minus. So what happens here is my OH minus, okay, they will react, okay, with my H plus. Okay, they will react with my H plus. So you need to first calculate first what is going to be your initial HOBr. So I'll just make it bigger, HOBr, to give me H plus and OBr minus. Okay, so initial HOBr, okay, you can see here the data given. So 20, so you can calculate N of HOBr, and this is initial. So this is going to be 20 times, okay, 0.2 divided by 1000, and that's going to be 4 times 10 times negative 3. That's going to be your initial. Okay, so if you follow ICE, so initial, okay, initially is going to be 4 times 10 negative 3. Initially there was 0, it was 0. Now after that, okay, after that, at equilibrium, okay, at equilibrium, you are going to have, okay, you are going to have how much HOBr. Okay, so the HOBr, they are going to react, okay, the KOH, okay, going to react with HOBr, okay, to give you, okay, if I erase this part, KBr, H2O, I think KOBr. Okay, you are going to get KOBr plus H2O. So it means one mole reacting with one mole. Okay, so here, when I have 1 times 10 negative 3, okay, they are going to react, okay, with 1 times 10 negative 3 here, okay, to give you this. So it means the HOBr is going to decrease. Okay, it's going to decrease because they are going to react with KOH. So here, okay, my if you look at equilibrium, okay, the changes that is happening over here is you are going to, okay, react with 1 times 10 negative 3, okay, which is going to be, you are going to get 3 times 10 negative 3. So, or you can say number of moles of HOBr at equilibrium is, okay, 4 times 10 negative 3 minus 1 times 10 negative 3. You are going to get 3 times 10 negative 3. That's going to be at equilibrium. Now, we need to also find out what is going to be the number of moles of BRO minus, okay, which is this one, at equilibrium. Okay, and this one is quite simple. Okay, so this one, they are going to give you, okay, this one is based on, okay, the KOBr that we have. Okay, the KOBr that we have. The KOBr, okay, if you can ask me why it's not coming directly from here. Okay, why it's not coming directly over here? We don't need to even use the ice over here, because for buffer, okay, for buffer, even though we know that, okay, they will dissolve to give you this and this, okay, but the amount that you are getting for this is too little. Okay, too little. So most of the OBr minus is coming, okay, from here. Okay, it's coming from here. So again, yeah, Lavi, you can go. So here it's going to be 1 times 10 negative 3. So KOBr supposed to give you K plus and OBr minus. So if you have 1 times 10 negative 3 complete, they will give you 1 times 10 negative 3, 1 times 10 negative 3 also here. So the number of moles of OBr minus at equilibrium will be the same. We are not including this. Okay, we are not including this. So it's going to be 1 times 10 negative 3. Okay, once we have that, okay, so we just need to find out, okay, what is going to be the H plus. Okay, so the H plus, okay, is going to be, we will look at the ratio. Okay, the ratio that you have over here is going to be 1/3. Okay, if you look at OBr minus divided by HOBr, that's going to be 1/3. Okay, so this one, okay, you can use the formula, okay, the buffer formula pH. Okay, if you want to use the pKa plus log salt divided by acid. Okay, if you want to use that, okay, you can continue using that. Okay, but if you want to use this method also, the one that is mentioned in the marking key, okay, 1/3, and then they calculate the H plus separately. Okay, that one is also possible. So whatever way that you use, okay, you will get, okay, so pKa that I'm going to use is going to be the pKa that I have. Okay, use the Ka over here. Okay, you can calculate the concentration of salt and acid. You can see this is the salt, this is the acid. So you can use log 1/3. Okay, pKa is going to be negative log 2 times 10 negative 9. And then you get. Okay, let me check the answer. Eight 8.69897. Okay, so if you calculate this, okay, you will get 8.9. Okay, can you check whether you get 8.22? I'm not getting the 8.22. the ratio is 1/3. H plus is 3 times 2 times. Okay, so if you are getting that, then it's fine. Yeah, so you are going to get, okay, the value. Okay, please check on the calculation again. Okay, so you are going to get, as long you mention, okay, here the correct answer, okay, is going to give you 2 marks. Okay, so the working is important. Okay, please remember they don't bother what kind of working that you are using. Okay, but the one that they have highlighted is you need to state these 2 working. Okay, whatever working that you do, as long you mention about this, then you can have that 1 mark. Okay, so this is going to be important also. Okay, please take note of that. Okay, so please use. Okay, but again, here they find the ratio. Okay, find the H plus, then they calculated the pH. Okay, so please you see also. Okay, what which of the ways that you can use, so that, okay, you can get the right answer. Okay, now for number 6. Okay, let's try number 6. Now, the elements in group 2, okay, include magnesium, calcium, strontium, and barium. Write an equation, okay, for the change representing the first ionization energy of magnesium. Include state symbols. Okay, so magnesium, okay, make sure it is in gas. Okay, this is very important. Okay, so it will give you Mg plus. Okay, and then it is also going to be in gas, and then plus electron. Okay, if you do not mention, even I don't think so, they need to say include state symbols. If they don't mention also, if you do not write the gas, you will not get the 1 mark. Okay, write an equation for the reaction with strontium and cold water. Okay, strontium do react with cold water, so strontium. Okay, if you are not sure, okay, you know, like magnesium. Okay, magnesium reaction with water, I think that's 2. Yeah, so you can have either MgO or MgOH. Okay, please read on this, because the reaction is going to be different. One is going to be H2O, okay, and then another H2O. Magnesium is special a bit, okay, because as you go down the group, okay, the reaction is going to be more vigorous, more reactive. So the one on top is not so reactive. So with water, okay, they can give you MgOH 2 plus hydrogen gas. Okay, but if you happen to increase the condition or make the condition more extreme, if you heat up or you put a reaction with steam, okay, so the reaction is going to be different. You are going to get MgO plus H2. That's the difference. But the rest of them, okay, the rest of them, they will follow. No need to have like, they will follow the normal condition, which is going to be the hydroxide. They will follow the hydroxide. So it means that strontium, okay, when you react with water, okay, they are going to give you strontium hydroxide plus hydrogen gas. Okay, this is going to be the equation. Since they mentioned about state symbols, okay, so you need to write the state. So this is going to be solid, and this is going to be aqueous, liquid. Yeah, okay, it's going to be liquid. Okay, liquid, and then this is going to be aqueous, and this is going to be gas. So the only thing that you need to do is to balance the equation. Okay, you balance the equation by putting 2 there. Not balanced also, you will not get the mark. Okay, please take note. Describe and explain the trend in reactivity observed in reactions of these group 2 metals with cold water. Now, this is what I mentioned just now. As you go down, okay, please remember the size is going to increase. When the size is increasing, okay, if you look at the electron also, the ionization energy is going to become lower. Why? Because it's easier, okay, to release the electron, okay, because they are further away from the nucleus. Okay, the electron, the whatever electrons, okay, they are further away from the nucleus. Okay, so less attraction. So in group 2, okay, we are talking about metals ability to lose electron. So we look at into ability to lose electron. So the reactivity, describe reactivity will increase. Okay, reactivity will increases down the group. Okay, and then you need to mention about, okay, because it's 1 mark. Okay, and then they also ask you to explain. Okay, so you need to explain and, okay, why. Okay, so you need to tell, okay, it is easier, okay, it's easier for the electrons to go out. Now, since they already mentioned about ionization energy, I think it, the best way is to relate with the ionization energy. Okay, so you can say it is easier. Okay, it is easier, or you can mention about the ionization energy. Okay, it's easier to ionize down the group. Or you are not sure. Okay, you want to use the ionization energy. Okay, instead of writing and it's easier to ionize down the group, you can say and the ionization energy, okay, ionization energy decreases down the group. Since it's only 1 mark, okay, so you can leave it like this, but normally I will include why, okay, because, okay, it's further away, okay, further away and shielded more, okay, from its nucleus. Okay, this is normally when I will write if it is 2 marks. Okay, if it is 2 marks given. Now, group 2 metal nitrates decompose when heated. Okay, so this will be the last question over here. So nitrates decompose when heated. Do remember, carbonates also decompose when heated. So describe fully what is seen. Okay, so you see nitrate, any kind of nitrate. Let's say I take one example, calcium nitrate. Calcium nitrate, when you decompose, you are going to get calcium oxide plus NO2 plus oxygen. Please remember, there's only limited reaction that generates oxygen directly. And one of the reaction is going to be the decomposition of nitrates. Okay, so they do give you all this, okay, but no need to balance. This is just to show you, okay, but again, this is colorless. Okay, this is going to be solid, okay, a white solid. Generally group 2 oxides are going to be white. Okay, so here this is going to be a brown gas, brown acidic gas. So here they are asking, describe what is seen. Okay, so there are 2 things that you can see. So you just write down the both things that you can see. Okay, so brown gas, okay, brown gas, and, okay, if you don't mention N, okay, you will not get the 1 mark. Okay, the brown gas and white solid. Okay, must mention white. Why? They want to test you, okay, about the group 2 oxides. Okay, they want you to know about that group 2 oxide. They are always white. Okay, now write an equation for the decomposition of calcium nitrate. Okay, so now they ask you to write, so just write down. So if they ask you to write down, then make sure, okay, you write down the state and also try to balance. So here, okay, you need to balance. Okay, so I just put 2, I put 4. Okay, so if I balance this, I'm going to put 2 here. So nitrates are aqueous. This is solid. This is gas. This is gas. But if you look at the marking key, they didn't emphasize on the state. Okay, if you have time, please do. Okay, please do include all that. Now, describe and explain the variation in thermal stability, okay, of the nitrates down the group. Now, this one, okay, please remember, yeah. Okay, please remember, this is not AS question. Okay, so if they ask you about this question in AS, they will give you only 1 mark. Okay, and you need to know, okay, why thermal stability generally for carbonates and nitrates, okay, it is going to be more stable. Okay, so thermal stability increases, okay, down the group. Okay, so 1, thermal stability increases down the group. This one you need to know whether it's in AS or A2. Okay, so this one must know. Then in your what is differentiating U, okay, and the AS is going to be the explanation. You must mention about that, okay, because now nitrates, okay, the size of nitrate is quite big, okay, so it's nitrate. So if I have magnesium nitrate, it's a small cation, okay. So if I have a bigger cation, okay, and then something like this, okay, when I go down the group, okay, what I can see, okay, I can see the cationic radius, okay, or the ionic radius, okay, increases, okay, or to be say, it's better because I'm not talking about anion, so I say the radius of cation, radius of metal cation or group 2 cation increases. And then if you look at the charge, okay, the charge are the same. Okay, so when the same number of charge is divided with the bigger radius, bigger volume, the charge density is going to be, okay, the charge density is going to decrease down the group. When this charge density is going to be decreasing, so this one you need to talk about ability of polarizing or the polarizing power. Okay, so you can see that, okay, as you go down, less polarization from the cations down the group. So if you have less polarization, this NO3, okay, they are not going to be distorted. Okay, so the NO3 minus is less distorted. Okay, therefore the bond remains strong and difficult to be broken. So therefore, okay, you require more temperature to break them. Okay, so this explain about, okay, the thermal stability. So here, what are the things that you must write? Okay, thermal stability increases. Okay, you need to mention about any of these two, radius or charge density. Okay, so let's say I'm focused on charge density. That's 1 mark. And then you need to mention about less polarization or less distorted. So anything that is, you mention either this or this, you will get the full 3 marks. So that I think, please try to reflect when you write down your answer. Are you going to write down all this? Okay, charge density. Are you going to talk about less polarization? Are you going to use this less distorted? Are you going to use these terms? Okay, very, very important. Okay, please reflect on that. Okay, the last one, okay, explain about, okay, solubility of group 2 metal sulfates. This one is quite easy, you know. Why? Because even you don't know, okay, group 2, it ends with barium. Okay, barium sulfate, every chemistry student, they should know barium sulfate is a white solid. Okay, so you can see as you go down, okay, sulfates, okay, sulfates generally, the solubility decreases. Okay, so solubility decreases. So you just need to explain less soluble. Okay, solubility decreases. Now, this one, the solubility decreases. This one I told you, okay, it depends on lattice energy and also hydration, enthalpy of hydration. So you just say, okay, as you go down, okay, the size, because of the size, your both lattice energy and hydration, they decrease, okay, decrease down the group, okay, or less exothermic. But which one decreases more? Okay, this one I want to ask. Okay, it's already 10:10. Sorry guys. Okay, let me actually finish this. Yeah. So Charlton, which one do you think will decrease more? Hydration or lattice energy, Charlton?
Hydrated.
Yeah, please remember this. Okay, this one is going to be hydration decrease more than lattice. Yeah. Okay, your hydration, okay, hydration decrease more than your lattice, and this is going to be making, okay, it's going to be making the enthalpy of solution, okay, to become more endothermic or more positive, because the more positive it is, okay, it's going to be less soluble. Okay, so this is going to become more endothermic. And I think I told you to come up with these ways to remember. I do not know. I forgot already what I asked you to remember. Each, is it SHL? I think, if I'm not mistaken, SHL, sulfate. Okay, for sulfate, the hydration decrease more than lattice energy. For hydroxide, okay, for hydroxide, okay, the lattice energy decrease more. Okay, so please remember this. Okay, SHL. Okay, SHL. Okay, sulfate hydration decrease more than lattice energy. But if they are asking for hydroxide, okay, why hydroxide is different? Hydroxide solubility will increase. Okay, so hydroxide solubility will increase. So you just need to tell, okay, this one increase. This is also going to decrease. Okay, but your lattice energy will decrease more than hydration. Therefore, your enthalpy of solution will be less endothermic. Okay, so that is going to explain about hydroxide. So please remember these two. Okay, okay, let's continue. Now, manganese, chromium, ruthenium are all transition elements. Explain what is meant by transition element. Now, transition element is going to be any element, okay, that can form, okay, that can form one or more, okay, one or more stable ion, okay, that is the term that we need to use, stable ions, okay, with incomplete d orbitals. Okay, incomplete d orbitals. So please take note, there are two things that you need to take note over here: incomplete d orbitals and stable ions. Now, so if we continue further, okay, so, okay, hold on. Okay, if you continue further, okay, they have mentioned that this SN 2 plus, okay, they can give you SN4 plus. They can by using oxidizing agents. So these are the two common oxidizing agents. Okay, potassium manganate, potassium dichromate. They're very common, okay, in chemistry. So when you are using this oxidizing agent, you are going to have SN2 plus changing into SN4 plus, which are going to be colorless. So now we need to describe the changes that we see when SN2 plus is added separately. One, okay, with dilute acidified MnO4, okay, and then dilute acidified Cr2O7. So it's an oxidation reaction. So what generally happens is MnO4 minus, they will change into Mn2 plus. And Cr2O72 minus, okay, the dichromate, they will change into Cr3 plus. it is very important to know the color change. This is going to be purple, they will become colorless. Okay, please take note. And this is going to be orange and they will change into green. Must remember. Okay, must remember. Now write an equation for the reaction between SN2 plus and acidified potassium dichromate. So to help you to write, I have written in advance. SN2 plus is going to become SN4 plus 2 electron. So this one you should be able to write down. Okay, no need to refer anywhere. Okay, but if you really cannot, then I think you are given your data booklet. You can get it from your data booklet, but you shouldn't be looking at the data booklet. I think you should know. Okay, Cr2O7, they must give you Cr3 plus. So I put 2 there, and then they must have water. So here must have H plus. So must have 7. So 14. So the rest is going to be 2 minus. Okay, 2 minus and 14 is 12. Okay, so the charges here is plus 6. So you need total 6 electrons to make it 6 and 6. So you should know about how to balance this. Okay, what is important now is to join these two equations together. These two half equations. Do remember that they have 6 electrons here. They only have 2 electrons here. So I need to times this equation by 3. So when I times that equation by 3, I am going to get 3SN2 plus. Okay. Then this one plus Cr2O7 2 minus. Okay. Plus 14H plus. The electron will cancel. So it's still 3SN4 plus. Plus 2Cr3 plus 7H2O. Okay. This will be the equation that we are going to look for. So you must make sure you write the correct equation. Okay, so in order to do that, you need to write the half equation and make sure you write the correct half equation. Now, ruthenium forms complex ions. In one such complex ion, X, okay, ruthenium ion has a coordination number of 6. Each of them, okay, has Ru2 plus and then Cl minus ion and one SO2 molecule. Now, they already give you, okay, a hit over there. This is a molecule, so it's a neutral molecule. And the remaining ligands are ammonia, so this is also neutral molecule. So the SO2 molecule acts as monodentate ligand, so only one coordinate bonding over there. And it is attached to Ru2 plus ion via sulfur atom. It means the sulfur is the one that is giving the lone pair of the electron to be bonded. So X exists in 2 isomeric forms. Okay, later we'll look into that. State what is meant by coordination number of 6. Okay, it means that they have 6 coordinate bonds. Okay, 6 coordinate bonds. Okay, coordinate bonds. Okay, but it's not enough to just simply say 6 coordinate bonds. You must say 6 coordinate bonds to where? To the central atom. Okay, in this case, this is not atom. This is going to be to the central metal ion. Okay, so please write it completely. They are asking, if you check in your marking key, they want this, this, and this must exist together to get the 1 mark. All 3 must be there. So 6 coordinate bonds, is it going to result in 1 mark? The answer is no. Okay, 6 coordinate bonds to the central metal ion. Okay, this is very important. Okay, now state the formula of X, include its charge. Okay, so we need to state the formula of X and include the charge. So here I have Ru2 plus, okay, and then you have 1 molecule over here, another 1 molecule over here, and then 4 molecules of ammonia. So I'm when I write down, it will be Ru, okay, then I have SO2, so I put SO2, and then I have Cl minus, so no need to put the Cl minus, okay, so it's still fine, just put 1 Cl, and then ammonia, NH3 is going to be 4, then you put a bracket. Now the bracket when you put, okay, you see the charge is going to be plus 2, this is going to be 0, this is -1, this is 0. So plus 2 plus -1, the charge is going to be +1. So you need to write down the charge of the overall molecule, overall transition complex is going to be plus. So this is going to be very important. Okay, so state the formula. It's all written over there. If you are wondering whether is it matter if I put like this in the marking key RU, then after that ammonium, they put 4, and then they put Cl, okay, then they put SO2, okay, bracket, they put like this. Now it depends, it's relative. Why? Okay, if I'm examining you, I will give you this correct, but the correct way to write this is going to be this one. Why I say this one is going to be correct? Because we follow alphabetical order. This is ammonia, this is going to be chlorine, and this is going to be sulfur dioxide. Okay, so sulfur, related to sulfur. So A comes first before C, then after that S. So they follow alphabetical order. Okay, so if you are wondering why it's slightly different, okay, this is based on alphabetical order. So if you want to, if you're rushing for your time, okay, it's fine to write it in this way. If let's say you have the time and you want to check it properly and you really need this 1 mark, okay, then I think everyone needs that 1 mark. Okay, please rearrange them according to alphabetical order. Okay, so don't follow N, yeah, don't follow N, it's ammonia. Okay, so it's not N, so it's ammonia, so follow that. Okay, that is done. Now draw 2 isomeric forms, okay, of X in the space boxes below. Okay, your diagram should show the 3-dimensional shape of 2 isomer and how each ligand is attached to the central ruthenium ion. So they want you to show, okay, and this is going to be a 3D diagram. Okay, please remember this one is still my working. Okay, this is still my working. I'm still wondering like how do I show? Okay, I have ammonia, 4 ammonia. How do I show using ammonia, 4 ammonia with SO2 and Cl? How do I show the isomer over here? The one that I can think of is going to be cis and trans. So how do I show cis and trans? So the only way that I can think of the 2 different groups that I have is SO2 and Cl. So I can put something SO2 here and put Cl, okay, make it a cross, okay. And then another one that I can think of, put SO2 here and Cl, put it side by side. And the rest of them is going to be ammonia. This is my working that I'm going to draw. So what I will do, okay, if I want to draw, okay, please remember it's 3-dimensional shape. So you draw accordingly like this, okay. So this one is going to be like this and like this, okay. Then you put Cl. This is ammonia. And then this one will be, you can draw like this. I'm sure you've seen many times already like this. Okay, and then this is SO2. And this is going to be ammonia. And draw, this is going to be ammonia as well. Ammonia. Okay, this is how you draw. And make sure, okay, they are connected properly. You can see here, the thing is they want you to make sure that each ligand is attached, okay, properly. So if you want a very good mark, okay, I will also suggest to be very careful with the one that you attach. Like for example, okay, if you have SO2, I will strongly suggest, okay, you put, okay, S, okay, you show they are going to be bonded to S. So it's going to be SO2. So maybe I'll just put O2 here, okay, so that it is showing that it is bonded to sulfur. And then this is ammonia. So ammonia like this, nitrogen here, okay. So I think it's better if you write it in this way. And then nitrogen here, so maybe like this, nitrogen here, maybe like this. So please write accordingly. So here, okay, if you do the same thing, I try to copy here and I put here, paste. Okay, so what I can change over here is going to be, I will change this, okay, this part, okay, because I want to show this is going to be trans, okay, so I want to show them cis. So how do I sorry, this is going to be, I am showing, okay, trans, correct. So this one I want to show cis, so I will show them, okay, maybe I put the SO2 there, Cl I put it here, okay, Cl I put it here, and then here I will put NH3. Okay, so this is how I draw. Okay, please be very careful with this. Okay, the important thing is how you show this. Okay, some of you might ask, okay, sir, do we need to show this thing? Okay, in this case, I don't see it drawn in the marking key. So please follow the one that I have drawn over here. Okay, so different arrangement, as long, okay, they do accept, as long that your Cl and ammonia, they are, if they sorry, the Cl and SO2, they are across, then it's trans. As long your Cl and SO2, they are side by side, then it's going to be cis. Okay, so that is going to be how they are going to give you the mark. Suggest the type of isomerism that you are having over here. The type of isomerism that we have over here, this is going to be cis or cis trans. Okay, or if you want to write down, you can say geometrical isomer. Only one, select only one. Okay, cis trans or geometrical isomerism. Now explain the origin of color in transition element complex such as X. Okay, this one we have done many times already. Okay, so it is 3 marks. Okay, so please take note, there are 3 important points that you need to consider. So I've written down some important points over here. Okay, when you have this kind of situation, okay, the presence of ligands, okay, will split the d orbitals. Okay, you must mention it's d orbitals here. They will create 2 sets of non-degenerate d orbital. It means different energy level. Okay, non-degenerate orbitals. And then when there is a light, okay, the electron, okay, they absorb the light, okay, the light energy, and they jump from lower energy, or the electron will become excited, okay, from the d orbitals from the lower energy, and they will jump to the d orbital with the higher energy. So this one is related to that. And this energy that is going to be absorbed from the light, okay, once it actually goes away, after they pass through the sample, they will transmit light colored, okay, which is going to be complementary to the color that we observe, okay, because it's complementary to the color that is going to be absorbed. Okay, it's complementary to the color that is going to be absorbed. So how do I explain over here? Okay, so important, okay, you need to say that the complex or the ligands, okay, the ligands, okay, they will make or split, okay, the d orbitals, okay, into 2 sets of non-degenerate, okay, non-degenerate orbitals. Okay, but please memorize, okay, d orbitals here, because I think we have tendency to say just orbitals. Okay, it must be d orbitals. That is the marks that is given also. So the visible light, okay, the visible light will be absorbed. Okay, will be absorbed by what? Will be absorbed by the electron. Okay, by the electron, where the electron will become excited. Okay, the electron will become excited or promoted. Okay, will become excited, and they move from lower degenerate d orbital to higher degenerate d orbital. Okay, when this is happening, okay, when this is happening, because of the absorption of the light, okay, so complementary color is absorbed. Complementary color is observed. Okay, based on the light, the frequency of light that is going to be absorbed. So 3 marks, d orbital, different energy, light will be absorbed, electron becoming excited. These are the 3 points that they are looking. Okay, if you are not sure, please refer to the marking key. These are the points that they are looking. Yeah. If you notice also, they don't use this degenerate orbitals also. Okay, they just say different energies. The meaning is still the same. Okay, so they have d orbitals with different energy. Okay, but in your textbook they say degenerate orbitals, so it's fine. Okay, you can use both. Now, number 8, protein are natural polymers. When one particular protein is partially hydrolyzed, the product mixture includes the tripeptide E. So this is going to be tripeptide. So here describe the condition that can be used to hydrolyze E to produce a mixture of 3 amino acids. So if you want 3 amino acids, okay, so we need to break the peptide bond. Okay, the peptide bond is going to be between this NH and then carbon double bond O. Okay, so we want to break that. Okay, so I want to break here, I want to break over here. So if that happens, you are going to get molecule number 1, molecule number 2, molecule number 3. So 3, yeah, 3 mixture. So we want to describe the condition. In order to break the peptide bond, okay, this bond can be broken based on three conditions. Okay, but out of these 3 conditions, please remember we didn't focus on this condition. Okay, I'll make it bigger. So this one is called hydrolysis. Okay, hydrolysis. So this hydrolysis can happen in either acidic condition, or they can also happen in alkaline condition. Okay, let me check whether you can still hear me. Okay, I know I'm a bit laggy now. Okay, but I just check again whether you can hear me. Okay, I think it should be okay now. So you see, I was talking about hydrolysis. Okay, so there are 2 types of hydrolysis. Okay, which is going to be acid hydrolysis, and we also have base hydrolysis. But we didn't really spend the time to go through this one. This one is by using enzyme. Okay, you can use protease, okay, at the temperature of 30 to 40, okay, around your body temperature. So this is going to be also possible, but we didn't learn so much about this. So I want you to either use this or this. Okay, dilute sodium hydroxide, okay, aqueous, okay, and then heat under reflux, or dilute hydrochloric acid or dilute sulfuric acid, you heat them under reflux. Okay, so you can use any of these. Okay, so you need to select one. Okay, so because the following question, okay, this question is related to A1. So let's say I'm going to use dilute sodium hydroxide, okay, aqueous, and then heat under reflux. So let's say this one is what I decided to select. So when draw the structure of 3 amino acids produced in this hydrolysis reaction. Okay, so you need to draw the 3 structure of amino acid. The 3 amino acids should be shown in the correct form for the condition you have chosen in A1. So please remember, it doesn't follow 100% in what is given in the marking key, because in the marking key they just show you the general part only. So your marking key it's just a guide. Okay, it's not the final answer. Okay, the final answer will be something like this, where when you are using dilute sodium hydroxide, when this one is broken, okay, so you see here, you are going to get this molecule, and then this part, okay, that I broke over here, you will get NH2. Okay, just put another H over there. So here, okay, once you have this amine and so on, when you react with sodium hydroxide, do remember sodium hydroxide, they do react with this carboxylic acid group. So this part, okay, so they will react, and the Na, okay, the Na will join in. Okay, so the Na will join in. So you are going to get the Na plus, okay, will come over here. You are going to get this salt. Okay, so the salt will be there. Okay, if you don't write the salt and you just put O minus, I think that is also accepted. Okay, but here, since I'm using NaOH, yeah, the Na will come over here. So that is going to be my answer. And if you look over here, this one is carboxylic acid. So again, carboxylic acid, they do react. Okay, this part, yeah, they do react with NaOH to give you the O and A. Okay, so you have O and A over there. So here the same thing, this one, okay, alcohol, okay, the alcohol group, when I react with the sodium hydroxide, okay, alcohol, okay, this one, wait, yeah, let me check. Okay, so alcohol, this one is my mistake. Alcohol do not react with sodium hydroxide, so it will stay as OH. Okay, do remember, okay, alcohol can react with Na. Okay, alcohol can react with sodium, but alcohol do not react with NaOH. No reaction. Okay, no reaction. But phenol, on the other hand, they react with sodium. Okay, and phenol, they also react with sodium hydroxide. Okay, please be please take note of this. Okay, phenol, they do react with sodium hydroxide. So you are going to get, if I put like this is phenol. When they react with sodium hydroxide, you are going to get the phenoxide ion, O minus and A plus, and then H2O. This is going to happen. Okay, but alcohol itself do not react with NaOH. Okay, this one I already mentioned to you earlier. Okay, about this, please take note. So here it comes over here into practice. Here, the OH do not react with sodium hydroxide. OH will be there, and then this NH2. This one is NH2. No reaction with NaOH. So you have that. So here, okay, you have carboxylic acid group over there. Same carboxylic acid. They will join, okay, with NaOH to give you this this compound. And then for this part, okay, NH3 plus, when I react with NaOH, the H plus will go here. They will join with the OH to give you water. Okay, so it means that the NH3 plus will become NH2. Okay, so that's why I put NH2. And then here, similar, okay, when you have carboxylic acid, okay, carboxylic acid, they do react with sodium hydroxide. Okay, so when I react, okay, I'm going to get this. Okay, so please take note of all these products, okay, when you do the hydrolysis reaction. Now, if a pure sample of E, okay, is obtained in aqueous solution, several different types of intermolecular forces are possible between pairs of E. So you see, there are a few different types of intermolecular forces that can exist, okay, when you have this. So what are the intermolecular forces that can exist? Okay, because you need to think, intermolecular forces, we have learned about permanent dipole-dipole. You have learned about van der Waals forces, okay? With the others not showing the salt. Aneta, what do you mean? With the others, like, it means that if it is going to be, if you are using HCl, okay, then it's going to be different also, Aneta. Okay, if you're using HCl, then carboxylic acid group will still be there, okay? But you know the NH2 over here, the NH2, they will react with the HCl. You are going to have NH3Cl. So you will not get the NH2 there. So please check accordingly. They will have different product. Okay, they have different products. So for if you are using HCl, then this part will be OH. Okay, but this part, the anything that has NH2, then they will have NH3Cl. They follow accordingly. Okay, so that's why they give you some kind of a general equation over there. Okay, so that you can follow. Okay, so if write NH3, do I still get a mark? If you simply write NH3, do you get mark? Do you get mark? I don't think so. Okay, but let me check the marking key, yeah, Aneta. 3 amino acid in any ionic or non-ionic states, 3 amino in the correct ionic state. Okay, you will get 1 mark, Aneta. Okay, but you will not get the full mark. Okay, so imagine you need to get, if you have anything wrong in one of this, then automatically 0. So it means everything is correct. Okay, you still use the NH3 plus, you will not get the 2 marks, you will get only 1 mark. Okay, please take note of that. Now, next, okay, so here they want to know the intermolecular forces. The intermolecular forces that are going to be there, okay, we have permanent dipole, permanent dipole, permanent dipole, dipole. We have hydrogen bonding, okay. We can have van der Waals forces, okay, but I think on top of the van der Waals forces, when I see this positive charge and negative charge over there, I think better to say that ionic bonding will be there. Okay, so they do accept van der Waals forces, okay, but I think here when you look at this diagram, automatically it's ionic bonding should be there. So I'm going to select this PDPD. Okay, what is PDPD? Is going to be permanent dipole. Okay, permanent dipole, permanent dipole dipole. Okay, permanent dipole dipole. And it is going to be between what and what. So basically PDPD is between anything that has delta positive and delta negative. So the one that has delta positive partial, yeah, not completely negative, completely plus. So partial negative, this is partially negative. Okay, partially positive will be example, maybe the hydrogen is partially positive. Okay, so that's going to be partially positive. So between NH and O, okay, then there will be a possible interaction. So do remember, it's not the same molecule. It must be different molecule. So we are talking about the pair between NH and CO. So if you want to give, okay, NH and CO. Okay, so they might have permanent dipole dipole. Hydrogen bonding, so you need to look for anything that has the H plus, okay, the partial positive of H. So partial positive of H can happen, I think here, partial positive of H, partial positive of H can. So then must be something with a partial negative, but it must involve O, N, and F. Okay, so I have oxygen there. Nitrogen is also there. Okay, so you can choose which one you want. Okay, so you can either write down NH and OH. Okay, NH and OH. So this is delta negative. This is going to be delta positive. Okay, so that is going to be hydrogen bonding. So the ionic bonding, so you need to tell, okay, this NH3 plus, NH3 plus, and COO minus. Okay, so that is going to be another one. So ionic bonding. So you see, when they give you the marks, okay, they are going to determine whether, okay, in order to get the full mark, okay, it means that in order for all this to be correct, you need to mention the correct pair. Okay, you need to mention about correct pair, and then you need to also mention about what like for example, if you just say ammonium NH3 plus alone, it's not enough. You need to mention the NH3 plus and COO minus. So you need to explain. Okay, if you have time, please explain. But I think the one that they want must have this together with this. Then only you can get 1 mark each. So you get 3 marks. Okay, if it is anything missing over there, you can see in the marking key, they mention both. Okay, they mention both. So if you don't write, okay, I don't think so you will get the marks. Okay, so each, even this one also both. So you need to mention. Okay, now next, okay, polyester and polyamide are two important types of condensation polymer. Draw the structure of one compound, okay, a compound that can polymerize to form a polyamide. Okay, polyamide. How do I get polyamide? Okay, I get amide linkage. What is amide? C double bond O and then NH. Okay, so this one is going to be amide linkage. So I get it from this C double bond OOH with anything that has NH2. Okay, I get it from that. So I need to find out a compound that can polymerize without the need of second monomer. Whenever they say without the need of second monomer, it means the compound itself has these two groups. So quite simple. Just put C, and then you put carbon double bond OH like this. Okay, this is going to be one part. If you want, you can put C. If you want another C, also doesn't matter. Doesn't matter how many C that you want to put. Okay, but make sure that the end of this you put NH2. So it doesn't matter how many carbon that you have. Okay, they just ask you to draw the structure. So doesn't matter how many carbon in middle you have. Okay, but okay, you must make sure that okay they have the carboxylic acid. You must make sure that they have NH2. Okay, that is going to result okay in a formation of this condensation polymer. Okay, can we write another type of answer? Yeah, possible. Okay, another type of answer that you can have is going to be you can also react. Okay, you can also react if let's say you don't want to put NH2, I can also react with Cl. Okay, so it means if I have like for example C double bond O Cl, and then I have NH2. Okay, then it's possible also because there is going to be you are going to get peptide linkage also. So here maybe another molecule that you can draw is maybe like this, and then Cl, C double bond O, Cl, C H, maybe C NH2. Okay, that is also possible. Okay, please choose which one you want. Okay, so you can either use the one that involves the carboxylic acid and then NH2, or you can choose the one that has the acyl chloride and NH2. It's possible. Next, okay, draw the structures of two different compounds that can polymerize together to produce polyester. Okay, with 4 carbons present per repeat unit. So draw the structure of two different compounds. Okay, so it means per unit must have two. It means 4 carbon atoms. So maybe what I do is I will take 2 carbon here, another 2 carbon here. So total when they join together, they are going to get 4 carbon atoms per repeat unit. So I can use a lot of combination. So maybe I can use something related to diol, okay, OH and OH. Then they react with something that involves the dioic acid. So they can also give you the polymer. Okay, this is going to be not in the same molecule. Now they are different monomers. Okay, you can also use this one. Okay, the carboxylic acid. Okay, sorry, because carboxylic acid, this one is quite vigorous. Okay, but here this is more reactive. So you can also use ethanol chloride. Okay, with the alcohol also, different combination. So if you want, okay, I will write down OH, and I will write down carboxylic acid here. You can write down different combination also. Okay, I will write down using different pen if I'm using different combination. So maybe I'll use OH, but here I'm going to use Cl, and then Cl. So also the same. So I'm using the 2 carbon and 2 carbon when you join, and then it's 4 carbon here. So please take note of that. Okay, so the rest you just put the hydrogen and everything. Make sure everything's properly done. Okay, I'll take this as my answer. If let's say the one circle, okay, if I want to give the name of the compound, this is going to be a diol. Okay, so what kind of diol? So this is going to be ethane. Okay, ethane 1,2 diol. carbon number 1, carbon number 2. So this one is going to be ethanoic acid, okay, but now you have 2, okay, so this is going to be named as ethane dioic acid. If let's say I choose this one, what is going to be this name? This one is going to be ethane dioyl chloride. Okay, that's why it's a bit difficult. Okay, I think better to use ethane dioic acid. It is inside your textbook also. Okay, next, number 9. Okay, the structure of butanban, okay, is shown. So butanban acts as a base. Okay, so if it is a base, okay, it's going to be a proton acceptor. So they can accept proton. So when they accept proton H plus, so it means base itself, they must have lone pair of electron so that they can donate the lone pair of electron to the proton. Okay. So here, the only thing that I can see over here that might have the lone pair, maybe this one. Okay, maybe this one also, they have lone pair. Okay. Even this one, okay, they have lone pair also. Okay. So complete the equation, okay, for a reaction where butanban acts as a base. Okay, so if you have in this kind of situation, you want to write down, I think most of the time I will select this one. It's much more easier, okay, to show it as a base. Okay, so let's say I'm going to react as a base H plus reacting with the proton. So what will happen? Okay, is going to be, I'm just going to redraw this. Okay, let me. So I just redraw this and then NH2, okay, but now it will become NH3 plus, okay, because H plus came in. And then, okay, if I draw the same way, so I have like this, O, okay, like this. Okay, this is going to be the equation. Now predict whether butanban is stronger or weaker base. So this one maybe I'll ask someone. Jody, do you think butanban is a stronger or weaker base than ammonia?
Weaker.
Okay, if it is weaker, why?
The nitrogen overlap with the benzene ring, so less able to accept proton.
Okay, it's correct, but not the nitrogen is overlapping. Okay, please take note. Okay, so the one that is going to happen is going to be the electron, the lone pair of electron. Okay, they will become delocalized into the ring. Okay, so the structure is going to be stabilized by the benzene ring over there. So it means that this lone pair, okay, since they are entering the ring, so it's not readily available. Okay, not readily available. If it is not readily available, so when H plus comes in, they cannot, okay, accept the proton. Okay, they cannot accept the proton easily compared to ammonia. So that's going to be the answer. So it's weaker. That's going to be 1 mark. Okay, weaker. Okay, but again, you need to explain. So if you don't explain, then it's going to be wrong. So you must say weaker because, okay, because the lone pair of electron at nitrogen, okay, is delocalized into benzene ring. When you want to mention about overlap, I think you need to say the p orbitals, okay, the p orbitals overlap with the p orbitals in the benzene ring. But I think it's not so clear over here if you want to look into that. So I think the best way is to say the lone pair of nitrogen, they become delocalized into the benzene ring, okay, making it less available, okay, making the lone pair less available for bonding with proton. Okay, compared to ammonia. Okay, that's going to be 1 mark. Now complete the reaction scheme below to show the structural formula of the products when butanban is treated separately with the stated region. Now if you look at Br2 over here, okay, the first thing I think you will be thinking is, where do the Br2 go? Okay, so because I don't have any double bond over here, so if it is Br2 just aqueous at room temperature, how come the reaction can continue? The reaction will continue, okay, because normally we think that if you have Br2, we need to have a halogen carrier, but okay, you do not need to have a halogen carrier because of the presence of NH2 over there. This NH2 will donate, again the same, the lone pair of electron of the nitrogen, they will enter the ring, okay, enter the delocalized ring, and they will become like make this ring to become more highly, the charge density will be more. So when the charge density is more, okay, the electrophile such as Br over here, they are going to be attracted directly over there, and they are quite reactive. It means they will be attached to the benzene ring without the need of halogen carriers. Okay, but you need to take note because they are electron donating group, okay, similar to CH3 and so on. So since because they are electron donating group, they will activate position 2, 4, 6. And you can see this position 2, okay, position 4 is taken, so 6. So it means when you draw this, okay, you are going to get something like, I will draw NH2. So here Br will come here, Br will come here. Okay, this is going to be the structure that we are going to look. Okay, so no need AlCl3 like what I written over there. Okay, now this is going to be the production of azo dye. Okay, the production of azo dye. It happens from temperature 0 to 10 degrees Celsius. Do not get this confused with nitration reaction. So this one is going to be, you need to form this, okay, from normally we form with NaNO2 plus HCl, then you get this and this one, okay, they will react with this phenylamine, okay, so when you have phenylamine, what is going to happen, okay, you are going to get a molecule, okay, I will draw the molecule. You are going to get the molecule that has the N2 plus, okay, so I put like this. This one I just put N2 and plus, it's enough already. I think last time, I do not know whether Gabriela, Nicole, or Arnetta was asking me about this question. Do we need to know how they really form N2 plus? No need to know. Okay, no need to know. Okay, the reaction is when this one comes here. Okay, the nitrogen over there. Okay, they are going to form this N2 already. So no need to know how it forms and so on. Okay, so this one you just need to memorize only. If you want to give the N2Cl, okay, it's fine. Okay, if you want to give N2Cl, it's fine also. Okay, so if N2 alone, then it must be positive. Okay, the next is going to be NaOH under reflux. Okay, so sodium hydroxide under reflux. Basically, we are trying to break the ester. Okay. So this one, this bond, okay, will be broken. Okay, so here when you do that, okay, you are going to have two products. Okay, so one is going to be this one. Okay, you can draw properly. Okay, I'm just roughly drawing. Okay, so I have this, and then OH. Okay, and then here you have another one which is going to be OH, then something like this. Okay, so this is going to be the structure. Okay, so you are going to get two compounds here, and because of the reflux. Okay, so again, okay, please take note, since you are using NaOH, okay, you cannot leave the answer like this. Okay, you have to do, okay, the carboxylic acid will react with the NaOH. So you need to erase this part and say there is O minus and Na plus. Okay, very important. Okay, even here in the marking key, they say O and A. Okay, if you write down also doesn't matter, it's still going to be accepted. Okay, so two things must be there. And then next, okay, the proton NMR spectrum, okay, of butanediene in CdCl3 contains one or more peaks that shows a triplet splitting pattern. Now, so for triplet splitting pattern, so you see here the triplet splitting pattern. This one, if you are using CdCl3, okay, we are going to use like there is more splitting, and it's also proton. Okay, so why there is a splitting? Because the carbon that is next to the proton environment, the next carbon that's next to the proton environment, they if they have the number of hydrogen, you need to use the n+1 formula for the splitting. Okay, so you need to consider about that. So for now, when I want to see like state the number of peaks in the spectrum that shows a triplet splitting pattern, okay, it means that I need to see where which of them, okay, which hydrogen environment is bonded to carbon that has 2 hydrogen, okay, because triplet. So 2 + 1. Okay, so I'm looking for anything that has the 2 hydrogen. So here, if I look at this carbon environment, hydrogen environment, this carbon is only 1H. Okay, so if it is only 1H, then when I put n+1, that's going to be 2 only. Okay, so that will not be the answer. So if I do further, like for example, for other hydrogens, okay, like for example, this hydrogen, for example, if I'm looking at the carbon next to it, okay, I'll share the screen again. Hold on. Okay, you can see the screen now. Okay, if I have this environment over here, I can see there is no carbon beside here. Okay, there's no carbon here, but I do have one carbon here, and then they have another 2 hydrogen. So for this environment, okay, for this environment, I have the one that I circle. Okay, let's wait for it to appear. Okay, it appeared. So if you look over there, okay, this environment, okay, they are going to have opposite to this carbon is going to be 2 hydrogen. Okay, because of 2 hydrogen, so 2 + 1 then is going to be 3. So for this environment, I am going to get triplet. Okay, I'm going to get triplet. So let's look at this environment. For this environment, will I get triplet or not? Okay, carbon, hydrogen, hydrogen. Now you see, for this environment, I have 1, 2, 3, 4. Okay, let me use different pen. 1, 2, this is carbon next to it. Another carbon next to it, 3, 4. You are not going to get, okay, triplet. You are going to get 4 + 1, 5. Okay, for this, you are going to get 5. For this, you are going to get 3. I hope you can understand this. Okay, and then for this one, this carbon H. For this environment, each of these hydrogen, they have the same environment. For this environment, the carbon next to it, okay, you have 2 hydrogen. So possible. This is also going to be 3. So how many of them, okay, they are going to have, okay, how many of them they are going to have 3 triplet? Okay, the answer is going to be 2. Okay. Now, Aneta was asking, sir, is it acceptable if we just use R as the R group, like NH2, R, CO, Cl? It's possible, Aneta. Okay, I think the one you're asking is the one that we simply put. Okay, but again, do remember, don't use the R in the middle. Aneta, so I advise you not to do that. Okay, why? Because NH2, if you put NH2, then RCO Cl, okay, because R is NH3, CH3 or C2H5. If you are referring to this one is CH2 only. So it's not suitable. Okay, it's not suitable. But you can use like this, CH2 bracket N. It's possible. Okay, CH2 bracket N, then you put NH2 here, and then you put COCl. Yeah, definitely going to be accepted. Okay, next. Okay, next. Here, okay, I was mentioning about just now. Okay, number of peaks. Okay, that shows triplet. So you are going to get 2. Okay, I hope you understand from this explanation. Yeah, this one and this one. Okay, I think here they will ask on the diagram of Butamban, show circle the proton responsible for the peak. So circle this one. Okay, these two, they because of this and this plus 1, so get 3, and then this 3. Okay, because of that. Okay, if you are still wondering about why this one and this one not there, okay, please remember this hydrogen 1 2. Okay, 1, if let's say I use a different pen, yeah, for this environment you have 1 2 3 4 5. So instead of 5, only 5 plus 1. So you have 6. Okay. So please remember, okay, they will combine. Okay, they will combine. So anyway, okay, describe and explain how the proton NMR spectrum in Butanban in D2O. So now you are using heavy water. Now, if you are using heavy water, okay, the difference is anything that has the NH or OH, they will disappear. Okay, the peak will disappear. So here I do have this peak over here, which is going to be responsible to the environment attached to nitrogen. Okay, so that peak will definitely disappear. Okay, so how do I explain that peak is disappearing? So you just say one less peak. Okay, which peak is that? So NH2 peak. Okay, NH2 peak. Why is that? Okay, because there is a proton exchange. Okay, there's a proton exchange or rapid exchange with the deuterium atom. Okay, so rapid proton exchange with D. So here, do remember 2 marks. Okay, if you don't say rapid proton exchange, also doesn't matter. You say one less peak, and that belongs to NH2 peak is good enough already to give you the 2 marks. Okay. Now the next is going to be the mass spectrum, the last one. Yeah, the mass spectrum of Butanban includes the 92 and 57. So if it is 92 and 57, please find out which one do you separate, because you can separate into like break here, then you get CH3 plus. You break here, then you have CH2, CH3, then this is going to be plus. So please find out which one will give you 92 and 57. So normally, okay, what I do, okay, because 92 is a big number, so what I do, I try to count this one. Okay, so this is going to be C6, okay, C6, and then there is NH2, so I put NH2 there. So one of the hydrogen will be gone, yeah, because C6H6, if it is substituted here, so H4, okay, so C6H4 and H2, then I break over here, so it's supposed to be plus. Okay, so see whether what you get over here, C6H4 and H2. So 6 times 12, you can use your calculator, plus 4, plus 14, plus 2. Okay, see what you get. Okay, you get 72 plus 4, okay, plus 16. So 20, 20, 72, 92. So yeah, you can have C6, H4, and H2 plus. This is going to be the answer for that. Then 57. Okay, of course, nothing to do with this. Okay, because 57 is supposed to be smaller. So must be something related to either here, 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 or here. Okay, so you need to count. Okay, CH3 is 12 plus 3, 15. 15 plus 12. Okay, so you keep on doing that. Okay, so I will get something like this. I think it ended 1, 2, 3, 4. Okay, so 1, 2, 3, 4. I think it ended from here to here. Okay, you can calculate yourself. Okay, when you do that, okay, you will get 57. So this is going to be CH3, CH2, CH2, CH2 plus. Okay, so do remember you need to put the plus over there. Okay, so that is going to be the M/E 92 and 57. Now on top of this, okay, let me teach you one more. Yeah, okay, one more. Okay, if they say is suggest M/E is not 92, 92 divided by 2. Okay, so it's 46, for example. If it is 46, you can also give your answer as C6H4NH2 2 plus. This is accepted. Okay, please remember this. Okay, why? Because you take this one 92 divided by 2, you get 46. This is also accepted. Okay, I want you to take note of this. Okay, so you can have anything. Okay, if you have 92 divided by 2 divided by 3, then you have 3 plus 10. Okay, so this one is going to be, they can also ask you on this. Okay, anyway, it's already 2:32. Okay, this one is done. Okay, so I will share this link, this video also. Okay, I will